let's now solve an example. All examples we solve, as you have already understood, are with small samples that we, in practice, that we usually don't use in statistics. So in statistics, normal sample size is like 100 or several hundreds of observations. And here we use just 5, 6, 10 observations. This is just for educational purpose, just to show you manually how we can use these methods we are discussing here. And so this example will also be an example with several small samples. So the example is a manufacturer of diet soda is interested whether the can color has any effect on sales or not. And so 16 stores of approximately equal size are chosen, and red cans are sent to 6 stores, yellow cans to 5 stores, and blue cans also to 5 stores. And the sales results are provided. So for the stores that received red cans, the results are 43, 52, 59, 76, 61, 81. So these are numbers of sealed cans in tens of cans. So 43 means 430. So number of sealed cans during a given period, like, I don't know, 1 week or 1 month. So then for yellow, the numbers are 52, 37, 38, 64, and 74. And for blue cans, 61, 29, 38, 53, and 79. So 6 stores received red cans, 5 stores yellow cans, and 5 stores blue cans. So the question is, can we say that can color has some effect on sales? So let's now solve this problem assuming normal distribution and using the Fisher's test. So let's assume normal distribution for the response. So in this example, the response is sales. The factor is can color, and factor levels are red, yellow, and blue. And so we now assume the normal distribution of the response. And here we have, so k is number of factor levels. K is, it's better to use this, right? So k is 3, and capital N, total number of observations, is 16. So we have 6 plus 5 plus 5. So we're going to test a hypothesis that that the factor has no effect, that all these taus are actually, we have only 3, so tau 2, tau 3 are zeros, so this means that can color has no effect. And the alternative hypothesis is that there exists some tau that is not zero. This means that can color has some effect. Has some effect on sales. So, if we use the Fisher's test, so what we are to do? We are to find sample means for each of our samples and the global sample mean. So, for the first sample, x bar 1 is 1 over 6 times 43 plus 52, so on, up to 81, and this is 62. Then, for the second sample, x bar 2 is 1 over 5 times 52 plus 37 plus 74, and it is 53. For the third sample, it is 52. And the global sample mean of the united sample, is 1 over 16 times the sum of all observations from 43 to 79, and it is 55.67. Okay, now we are to find expressions that we have in the numerator and the denominator of the test statistic. So as for the numerator, we have 1 over k minus 1, that is 3 minus 1, and here we have sample size of the first sample, 6, multiplied by the sample mean of this sample, that is 62, minus global sample mean, 55.67 squared, plus the same for the second sample. So 5, the sample size, times the sample mean for this sample minus global mean, plus the same for the third sample, So, and the result is 171.65 approximately. This is the numerator. Then the denominator is 1 over n minus k, 16 minus 3. And here you are to calculate the sum of 16 terms, like starting from 43 minus the sample size of the first sample, 62 squared, to the last one, 79 minus the sample size of the third sample, that is 52 squared. So this is the sum of 16 elements, and its value is 277, approximately 277.54. Then the test statistic is found by dividing this by this. So it is 171.65 divided by 277.54, and this is approximately 0.618. So then we say that under the null hypothesis, the test statistic follows Fisher's distribution. Fisher distribution and number of degrees of freedom is k minus 1, that is 3 minus 1, that is 2, and n minus k, that is 16 minus 3, that is 13. And so we have right-tailed critical region, and the border is the quantile of the Fisher distribution, the quantile of the level 1 minus alpha. So as alpha is not provided, let us assume standard alpha 0.05, a standard significance level, default one. So, and here we have the quantile with 2 and 13 degrees of freedom of the level 0.95, and the quantile is equal, so we can find it in the table of the quantiles of the Fisher distribution. The quantile is 3.81. 3.81, and so we see that the test statistic is in the acceptance region. So the test statistic is here, it is 0.618. As the test statistic is in acceptance region, so this means that we accept the null hypothesis, and the null hypothesis is the hypothesis that Kahn-Keller has no effect. So what is our answer to the question we were asked? So can we say that Kahn-Keller has some effect on sales? We say no at the 0.05 significance level. So the answer is no at 0.05 significance level. So this is the solution when we assume normal distribution of our observations. Now let's solve the same problem without assuming the normal distribution using the Kruskal-Wallis test. So what we are to do here, first step always is to formulate the hypothesis, and the hypothesis is the same actually as in previous case. So the null hypothesis is that all taus are equal to 0, and this means that can color has no effect. No effect. And the alternative one is that at least one of them is non-zero, and this means that the can color has some effect. So after we know what we are testing, what hypothesis we are testing, so the first step when we apply the Kruskal-Wallis test is to rank our observations. So we have 16 observations, and we are to rank them. So which one is the least? This one, 29, is the least one, so its rank is 1. Then I have, I guess, 37. 37, its rank is 2. Then I have 38 twice. So they share the third and the fourth places, and that is why their ranks are between 3 and 4. 3.5 is the rank of this, and 3.5 is the rank of this. Then I have 43. 43, and its rank is 5. Then 52. 52 twice, so their ranks would be 6 and 7 if they were different, and so actual rank is between 6 and 7, 6.5 here and 6.5 here. Then I have 53, and its rank is 8. Then 61 twice, 59, 59, and its rank is 9. Then 61 twice, so their ranks are between 10 and 11, 10.5. Then 64, its rank is 12. Then 74, 13. 76, 14. 79, 15. And 81, 16. So the united sample is ranked. Now we are to find mean rank for each of 3 samples we have. So R bar 1 is the sample mean rank for the first sample. So 1/6 times 5 plus 6.5 up to 16, and it is 10.17. Then the sample rank for the second sample, mean rank for the second sample, 1/5, 6.5 plus up to 13, and it is 7.4, and the mean rank for the third sample is 1/5. Here I add numbers from 10.5 to 15, and the result is 7.6. So these are mean ranks for our samples, and now I can find the test statistic H. So H is 12 divided by capital N, that is 16, times capital N plus 1, 16 plus 1, and here I have, so the sample size 6 multiplied by the difference, square difference between the mean rank for this sample, 10.17 for the first sample, minus n plus 1/2. Capital N is 16, 16 plus 1 is 17, 17 divided by 2 is 8.5. So 8.5 is n plus 1/2. So then, plus, for the second sample, we have 5 multiplied by 7.4 minus 8.5 squared. And for the third sample, 5 times 7.6 minus 8.5 squared. So this is the formula for the test statistic, and the final value, if we do all necessary calculations, is approximately 1.18. Now we say that we know that under the null hypothesis, distribution of the test statistic is chi-squared with number of degrees of freedom. Number of degrees of freedom is 3 minus 1, k minus 1, k is 3, so it is 2. And for the critical region, we are to find the quantile chi-squared quantile with 2 degrees of freedom of the level 0.95, if we still use the standard significance level, and we do so. And so if we look for this quantile, the table, we will find that it is equal to 5.99. And the test statistic is 1.18. So we got the same result as in previous example, as when we assumed the normal distribution for our observations, for our response. Still, the test statistic is in acceptance region, and so the null hypothesis is accepted, and so the answer is absolutely the same. So can we say that can color has some effect on sales? No, we can't at the 0.05 significant level. So the answer is the same. No, we can't at 0.05 significance level. So that is how we can solve one-way ANOVA problems, assuming or not assuming normal distribution of the response we are measuring. Let us now solve an example using John Keir's trend test. And let this be the example I have already mentioned when we are interested in salaries of people with different educational levels. So let us say that we have 4 levels of education: primary, secondary, professional, and higher. And so the salaries are, we have 6 people, 6 random people with primary education, 6 with secondary, 6 with professional, and 6 with higher education. And so their salaries are, for those with primary education, 32, let this be 1,000 of rubles in a small Russian city, let's say so, 24, 41, 37, and 23. For the secondary education, 37, 29, 31, 45, 54, and 25. For professional education, 47, 39, 52, 41, 37, and 51. And for higher education, 65, 78, 59, 63, 72, and 66. So, and the question is, can we say that the higher educational level is, the higher salary is? So, can we say that the higher education is the higher salary is? So, our hypothesis is that the education has directional influence, directional effect on the response, and the response is the salary. So, this is the, so we use John-Heer or John-Heer-Terpstra test. Our hypothesis is, the null hypothesis is that our taus are all zeros, and this means that education has no effect. And the alternative one is that we have a directional effect. So the alternative hypothesis is actually what we are asked about. So the higher education is, the higher salary is. The higher education is, the higher salary is. So, now, when we use John-Heer-Terpstra test, we are to compare every observations with all others. And when we compare, if the number that is to the left is less than the number that is to the right, we add 1 to our counter. If they are equal, we add 1/2. If the one that is to the left is greater than the one that is to the right, we add 0. Don't add anything. So let's try to do this. I'll compare them one by one, and I'll write down So counters, when I finish comparing one number with all numbers it is to be compared with. So let's start with this. 32 less 1 greater 1 greater 1 less 2 less 3 greater 3 less 4 less 5 less 6 less 7 less 8 less 9 less 10 less 11 less 12 less 13 less 14 less 15. So 15. Then 19. 19 is the least observation, and so here totally we have 18 observations, and they are all greater than 19. So I can say that, so plus 18. Then 24. And 24 is also less than all these. So the least of this is 29. It is greater than 24. So plus another 18. Then 41. Greater 0, greater 0, greater 0, less 1, less 2, greater 2, less 4, greater 4, less 5, equal 5.5, greater 5.5, less 6.5, less 7.5, less 8.5, less 9.5, 10.5, 11.5, 12. 12.5. 37 equal 1/2, greater 1/2, greater 1/2, less 1.5, less 2.5, greater 2.5, less 3.5, less 4.5, 5.5, 6.5, equal 7, less 8, less 9, less 10, less 11, less 12, less 13, less 14. 14. 23. 23 is less than all these numbers, so plus 18. So that's all with the first column. Now I go here. So less 1, less 2, less 3, less 4 equal 4.5, less 5.5, 6.5, 7.5, 8.5, 9.5, 10.5, 11.5. 11.5. Then 29. 29 is less than these numbers, and we have 12 observations here, so plus 12. 31. 31 is also less than all these numbers, so plus another 12. 45. Less 1, greater 2, less 1, greater 1, less 2, greater 2, greater 2, less 3, less 4, less 5, less 6, less 7, less 8, less 9, plus 9. 54. Greater 0, greater 0, greater 0, greater 0, greater 0, greater 0, less 1, less 2, less 3, less 5, less 6, less 7. No. 1, 2, 3, 4, 5, 6, plus 6. 25. 25 is less than all these numbers, so plus 12. Then I go here, 47, less than all 6 numbers I see here, so plus 6. 39 is also less than all these numbers, plus 6. 52 is also less, plus 6. 41 plus 6. 37 plus 6, and 51 is also less than all this, plus 6. So if I add all these numbers, so that's all with comparing. Now I'm to add all these numbers, and if I do this, I'll get that the value of j is 193. Now I'm to find the expected value and the variance. So E of j is 1 over 4, according to our formula, then 24, and 24 is capital N, squared, plus, and here I have 6 squared plus 6 squared plus 6 squared plus 6 squared, and this is 108. Then variance. The variance of j is 1 over 72, and here I have 24 squared times 2 times 24 minus 3 minus 6 squared times 2 times 6 minus 3, and this is repeated 6 times as we have, as sample sizes are 6 for all samples. So 4 times and finally this is 387. Now it's time for the standardized j. Standardized j tilde is j. So j is 193 minus the expected value, 108, divided by the square root of the variance of j of 378. So, and if we calculate this, the value of j tilde is 4.38 approximately. 37, I'm sorry. 4.37. So, and now what is left is to construct the acceptance and the critical region and to give the answer. So we know that under null hypothesis, we assume normal distribution for j tilde. By the way, for samples of such small size as we have, so we have only 24 observations, frankly speaking, this is not enough. The sample is not so big to assume normal distribution. So the distribution of j tilde is asymptotically normal. This means for big samples it is normal. So actually we cannot assume normal distribution for such a small sample, but let's do this because I show you what do we do with big samples in practice. In practice we usually have big samples. So this is the critical region, this is the acceptance region, and we need the quantile 0.95 quantile of the standard normal distribution. If we assume standard alpha 0.05, then we have here z1 minus alpha, so 1 minus alpha is 0.95, and z 0.95 is 1.65, and the test statistic is 4.37, so J tilde is 4.37. So what does it mean? It means that so as J tilde is in critical region, this means that we reject the null hypothesis in favor of the alternative one. And the alternative hypothesis is that the higher education is, the higher salary is. So the answer to the question we were asked is yes. Yes, we can at 0.05 significance level. So the answer is yes at 0.05 significance level. So that's all with one-way ANOVA.